What I'm going to talk to you about today is math education. In fact, I'm going to start with math education, and I'm going to end my talk without math education. And it's really important to understand why I chose this title, Seeing the Way to Succeed in School Mathematics, because the key word here is seeing, because currently in our math classrooms, we do a lot of watching. Have you seen the movie Arrival? Yes. If you haven't, you should go see it. And you're probably wondering why I'm asking you if you've seen the movie Arrival. If you sit in a theater and you watch a movie, and you really like it, sometimes you go see it a second time, a third time, a fourth time, some of us go see it 20 times. Does that make me capable of making that movie? Not at all. I can sit in that movie over and over and over again, watch it very carefully, and really at best all I can do is learn the script by heart. But I will never be able to see how to make that movie. And that's exactly what we do in mathematics classrooms, is that we sit children in mathematics theaters and ask them to watch mathematics movies. For example, the multiplication table, over and over and over again, and then expect them to know multiplication, or know how we built that table in the first place. So what they do, in effect, for those who succeed in memorizing the multiplication facts, is that they've learnt the script at best. They haven't been behind the scenes to know how to make a multiplication table. So that's the problem. That's the main problem with our education right now in mathematics, is that we get the children to watch, and so they don't see behind the scenes. So let's see how that works. What's this number? I can't hear you. 47. Thank you. What about this one? 123. What about this big one? And in fact, I can keep throwing numbers at you and you will know them, or at least I hope so. And that's because you've learned, or you've sat in that mathematics theater and you've learned what we call the whole number decimal numeration chart. That's the script. So they put the script in front of you, you've memorized this. So the first number on the right is going to be your ones, and then the tens, and then the hundreds, and then the thousands, and so forth. And you've learned this quite well. But you didn't learn how this chart was created. Again, this is the movie and not the behind the scenes. So what we'll do is we will go behind the scenes to see why that is not working. In fact, that's what's making a math education not working. So we're going to write a script, because when you go watch a movie, the script is didn't just appear there. Somebody actually wrote the script. So I'm going to do a little activity. My earrings are clicking, eh? Take them off. Okay. It's also a strip show. So we're going to use the numbers you know. I'm not going to do something crazy, because most people I know are not comfortable with mathematics. So we're going to choose the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'll use T for 10. And notice there's no 0, right? We'll get rid of 0. In fact, historically, 0 came really late 16th century. So we're just going to use these numerals now. And I want you to write, or think in your head, how you would write the numbers 8 to 22 with these numerals. All I've changed is to remove a 0 and put in a T for 10. Well, you're probably thinking, this is how we write 8. This is how we write 9. This is how we write 10 now, because we have a symbol for that, which is called T. And then you probably say, oh, go. Pretty easy, let's go on. T1, because 10 plus 1 makes 11. T2 for 12, T3 for 13, all the way to 19, which you probably think, oh, T19 makes sense. Then you get to 20. Then it's TT, 10, 10, that makes 20. 10, 10, 1 for 21. 10, 10, 2 for 22. When I ask this question to my student teachers, they always give me these answers, because that's what they learned, is that they learned the script, but they don't really learn how to write a script. In effect, this is what is truly what we should be writing. So 8 for 8, 9 for 9, T for 10, 11. Now, why is it I'm writing 11 this way and not with a T? Well, if you look at the T in the T1, the T is in which column? It's in the tens column. So in effect, that T1 represents 101, not 11. When you look at 11 with just 1, 1, you don't say 1 plus 1. You're not adding the digits together. You realize that the first one on your left is telling you how many tens. So I have 1 10, and then I have 1 1. So that makes 11. So 12, 13, 14, all the way to 19. So how do we represent 20 without a 0? Well, it's simply 1T, because I can put 10 ones in one column, and then after that I put, sorry, I'm going backwards, 10 ones in one column, and then I simply need one more 10 to account for the 20 objects. And then 21 would simply be 2 1, 2 tens and 1 1, and 22 will be 2 2. The bottom line here is how we write a script. We learn what's the system behind it, and in fact, we should be creating those systems. So how do we write 100? I have 2 zeros to contend with here, so all I'm going to do then is simply use my T for 10. So if I have 10 in my ones column, how many more do I need? I need 9 more tens to make 100. And so it writes 9T. So what is going on here is that I'm working behind the scenes. And so instead of telling them, here's the chart, here's how it's built, and this is how you place numbers in it, we need to engage the students in building that chart. So understanding how we build that chart. So we start with ones. So let's say we use popsicle sticks. Then after I have ones, counting by 1 is very tedious, especially if I have a large amount of things. And so I'm going to group them and then count the groups. So I'm going to make a bunch of popsicle sticks. Here I chose 5. So I bunch my 5 popsicle sticks, and then I can simply count bunches of 5, because it's much more quick to do that. And then I will regroup, because even if I have a large amount of popsicle sticks, grouping them by 5, I'm going to end up with the same problem of having many groups of 5 to count, and so therefore it's not efficient. So I'm saying, okay, so when I have 5 bunches of 5 popsicle sticks, I'll stick them in a bag, and then I can just count the bags. So what we've done cleverly is develop this system of counting that is so efficient. It's become so efficient that we don't remember how we created that system. Then we have to use symbols to code it, either verbally or in writing. So if I'm counting popsicle sticks by bunches of 5, I'll need 0, 1, 2, 3, 4. I'll never see a 5, because the minute I have 5 things, it becomes one bigger object. And then we've introduced place value. So in here we have sticks, then we have bunches, then we have bags, and then we'd have boxes, crates, and so forth, right? So this is what our system is built on, this idea of these points here. This is how we've developed this whole chart in the first place. So when we present children with simply this chart already made up, they don't get to see behind the scenes. They get to watch. So it is a time for change. And we know for over 100 years now that we're failing children in school, in mathematics. And in fact, a lot of adults end up not liking mathematics and choosing careers that, to make sure that they don't have to have any mathematics. And so it has a large impact. And really, it's just a change in the way we do things, or the way we approach the teaching of mathematics. Now, the results and methods of mathematics are its artifacts. They're the movie that we go sit to watch in a theater. The actual mathematics lies in the thinking that creates those artifacts. So again, it's behind the scenes of the movie that the mathematics is actually occurring. And those artifacts are indeed surprising, just like Arrival is a beautiful movie to watch. But that's not what we want. We don't want kids to become really good at watching movies or watching mathematical results. We want them to become mathematical thinkers. So some of those artifacts are surprising sometimes. We discovered with our creative thinking that there are irrational numbers. Now, those numbers were accepted only about 150 years ago, so it's not unusual for learners to have struggles to understand these particular kinds of numbers. No one here doubts that even if they hate math, it is practical. It serves practical purposes. So for example, the Pythagorean theorem is used in construction. To paint your wall in your room, you need to take some measurements and know how much paint you're going to need. So mathematics is practical. But if you speak to most mathematicians, they'll tell you mathematics is beautiful. How many of you think mathematics is beautiful? Very good. Well, I do. I find it surprising, and it's practical, but it's also beautiful. Here's my favorite formula, it's the Laplace transform. How many of you are familiar with this one? No, a few, okay. The Laplace transform is a formula that takes a very complex problem and converts it into a simple problem to solve. It's a very powerful, formula, and that's what makes it beautiful. So I'm talking about mathematical thinking. So well, how do we do that, and what is it? So mathematical thinking is a whole way of looking at things, of stripping them down to their numerical, structural, or logical essentials, and of analyzing the underlying patterns. It's a way of looking at the world, seeing the world in ways that you can size things, you can time things, you can measure things, you can see the patterns, what's the same, what's not the same, the relationships among things. That's what mathematical thinking is all about. But if we teach a script, in other words, we keep plopping these kids in the mathematics theater instead of having them work behind the scenes, then we get the results we get for that, right? I was in grade 1 working with grade 1 kids this year, and I asked them a very simple problem. I gave them sequences of numbers. 3, 4, what number, 6, 7, 8. I also put the box at the beginning. What number comes before 4, 5, 6, 7, and I even put the box at the end. 2, 3, 4, 5, what number comes after that? Well, I wasn't surprised, but the teacher certainly was. This is what they answered. They put 1 in all the boxes. And that's because the script is you count 1, 2, 3, 4, 5, 6. So for them, no matter where it was, you have to start the script at 1. And I have lots and lots of examples of this, of children who watch mathematics instead of being interactive with the mathematics, they give you these kinds of results. But can we get kids to think? That's a good question. There's a lot of debate right now about thinking skills, cognitive ability, executive functions, and so forth. And I've been working closely with children all my career, and I can tell you that, yes, it's actually easier to get them to think than my adults. So absolutely, we can get them to learn to think. And once we get them to learn to think, then we know that they can develop mathematical thinking. So we need to be sure that they can think first. I'll give you an example. At the beginning of the year, I gave them these figures, very simple shapes, squares, circles, and triangles, and I asked them to look carefully with their eyes to see what is different. One of them is very different from the others, and they responded immediately. Some of them said A, some of them said D, some of them said C, and then when I asked them why they chose that one, they said, why not? I said, but look, just look very carefully with your eyes. See what's the same, what's not the same, you know, and they just looked at me with blank looks. Okay, well, it's B then. No, I don't want you just to give me an answer. I want you to look carefully at this. And they didn't seem to understand what I was asking them to do. So we did some more activities where they had to observe and discern what's the same and what's not the same and so forth. And they got better at it. They got so good at it that they surprised me. After about 4 sessions, I gave them another similar problem, but this time I threw in some noise. In grade 1, they're learning language. So they're learning how to read and how to write. So I presented them with letters, which had nothing to do with the task, but it was just to add some noise to see how well they would do. And I asked them which one of these doesn't belong. I'm a math person, so I know it's W because W has 4 lines, and all of the other letters have 3 lines. Most of the children picked W, and I was quite happy. But then I asked them why, and they said because it starts with a D. And I went, okay, can you explain that to me? And they go, well, A, F, N, H, W, D for W. I went, oh my goodness, that is so smart. I was thinking simple numbers of lines, and instead they came up with something a lot deeper using their language knowledge in order to look and see what's going on with these letters. So absolutely, we can change from not having a clue what to do with the task to actually coming up with something that surprised me as a researcher. And that brings me to my conclusion, and the idea that I'm trying to push, that I've been trying to push for a great many number of years, is that instead of teaching mathematics, what we should be doing is teaching mathematical thinking, which of course requires thinking. So we need to go away, walk away from mathematics education and start looking at educational mathematics, so that the kids are using mathematics really to learn about seeing the world. And we're back to my movie Arrival. So I thank you very much.